So, now we are going to switch topic a little bit again. I said before that it's hard to handle all the files and making exchange between them and store it in a consistent way. There is actually a solution for that, and that's databases. Actually, pretty old technology, and in principle, a traditional database is based on tables, and there are relations between these tables in some different ways. And here we have an example where we have animals and cells. So the animals are identified with some ID, and they have a weight, each of them. And then there is a relation to this, that we have another table where the animal one has some kind of cancer. There is some anisotropy value and the volume, and this would be the second table, and with those you can combine and making queries to get the information you want. And the old language used for this is SQL, or written out as SQL, and it's has been used since long time. I think even in the 70s it was defined. I'm not sure about that. But what you can do in it is you can search and you can add information. And there are different forms of it, also different implementation. These databases, so there is this SQLite, MySQL, and Hive are different services that can be used. And these can also be set up on easily on a Linux system, and then you can run your own local database if you like to try and test these commands. And typically what you have in a basic query is you write a text line like this, like select volume from cells, referring back to, no, sorry, too far, to this one. So here you have in the cell table, you have a volume, and that is what we are referring to here. So from a select volume from cells, and then you get the whole column of volumes from the cells table. Then you could also make a little bit more interesting query. So the average volume from cells where type is cancer. So here you can set extra criteria on these. You could also make combinations between different tables, so that you would bring in a certain selection of mice, maybe with some extra gene active or something, and then make this query together with that. So you can do it in different packages. You can get actually can import a SQL database into Excel, or you can also import it into a Pandas data frame. But also these things, they could in principle be done directly in these solutions. The difference is that the database is a service, and then you can access it from different places, which makes it convenient if you do distributed computing. Of course, you can also make more complicated queries, like here is what I said, where we get volume from cells where animal is within some range. For example, the weight is in the certain range, and then you can combine it even more to get some average cell volume from all mice. Then you have to join and connect different things. There are tutorials on how to use SQL. I use it so rarely myself, so when I need a query, I actually ask the chat to help me out, because I don't know it by heart, so I'm cheating a bit there. But for the few queries I do, this is sufficient. They are masters of SQL, and they can do quite a lot. Then you can go beyond SQL, which is then called NoSQL, and that is optimized for the new criteria that we have when we come into big data. That is not only single table columns, but it can also be like clusters or tuples of information that then can be better or more easily accessed when you have these connections. And one typical that is used is called MongoDB. That is used for this purpose, and you can also, there are also some graph network, so the connectivity is not one-to-one, but it can be nested in some kind of graph structures. Then we are talking about graph databases. So this slide I think I have shown a couple of times already, but it's still relevant, in particular when we're talking about the computing infrastructure. So what we need is the 3 V's: velocity, volume, and variety. And for that, we need to be performant. We need to process in reasonable time. We need to be able to scale. If the data is larger, we need to be able to scale our code and analysis workflow. And that is, in a way, also requires that it's flexible to change small details in the analysis. So ready for big data is when you can process loads of data with minimal extra effort, if you do 10 or 1,000. Same amount of effort is probably a bit optimistic, but anyway, a minimal extra effort. And big data, they're always claiming that they need so many data. So big data is when you're starving for data. In some cases, here the director of AMP Lab said that the limiting factor is actually the available data for learning their models. Of course, an important thing is no clicks per sample. As soon as you're clicking, you have an extreme delay point in your processing workflow. So minimize this, and in principle, the click should be replaced by some kind of parameterization or pre-processing that actually removes this required click state. So the big data problem is, of course, Google is a big consumer of data that they need to analyze, and they have peta and exabytes of data of website information that they want to analyze, and they want to know how often a page or how much linked a page is, and they implemented or introduced this PageRank algorithm to evaluate the quality of different websites. And in principle, what they want to do is run through every site on the internet, which is a huge amount, and say that the current site has a rank, which is some kind of PageRank function given this current site. And then you need to distribute this task and give all the computers some task to run, but the question is how. So what it does is it runs a couple of loops for every site on the internet. They want to compute the PageRank object, and then for every other site on the internet, they want to see if that page is linked to another site, and that would be the adding function here. And in the end, you get this PageRank for the site. The problem is this algorithm has the complexity big O n squared, which means astronomical times to complete just a single run, and they want to run it frequently, daily, hourly, to update their page rank quality estimate. So how to divide it? Maybe one would be to divide it up into language sites or regional sites. So we have English sites, Chinese sites, and run the page rank between them. But the problem is some of these, they link to each other, so then you would have some kind of strange gap in the knowledge. You could buy a really, really big computer, but one loop would take months, so that's not a good idea. So what they do instead, what even gets more is that we have again the failure problem, that if one computer or hard drive crashes, then you need to have computers to back it up, but you cannot have full redundancy, so you need to have a plan for that as well. But yeah, and maybe even a whole computer system is going down due to an earthquake, which could happen around Google because they are just on the San Andreas rift. So yeah, that could happen, but let's hope not. And on top of it, PageRank doesn't only count pages; it also uses the old rankings for the page and run it several times until the ranks converge. So it's a really complex system that needs to be handled. So what they do, they introduced something called MapReduce. So it's actually an algorithm or approach that has two steps. One is map, so that is relating the current information to some function. Here is a very simple example where we do have this data vector, and the mapping function is a squared value. So the map of a function of f on the L vector gives us the square numbers. Reduce is packing everything together, and here we have the sum function, and it's only taking two values. So we have a plus b. And to reduce, we can have different strategies. We can call them like this, just a bunch of this g function. So first g of 1 and 2, and then do the result comes with 3, the result comes with 4, and the result comes with 5. You can also split it up like this. So you have two of these g functions in together like this, and then the last one comes hanging in alone, as it is an odd number of items. Right now, it looks like we have the same number of calls, but it could be more efficient to do one or the other way. So that is a little bit of the reduce strategy on the vector. So what we do is we have this MapReduce, which takes partitions some input data into chunks and distributes it on all computers, apply the mapping on each element, and then we do some shuffle and repartition or grouping the data, then running the reduce on each group, and then collect the results and write to disk. All this is written like this as a job where we have the data, we have the mapping, and we have the reduce function, and those are put onto the server. And one thing we can do is, for example, key value pairs and grouping them. And important thing is that key must be comparable. Could be a number, could be a string, or some other kind of ID value. And that is used to group the data or sort the data in some sense. And then we have some value related to that. An example would be to counting words, where we have the mapping function. Then we do, in principle, we split a string for all the spaces. That would give us a list. And for every the mapping would be that every word gets connected with the number 1. That's just because that occurs one time at this place. And then we can group them together and do the reducing, which adds the values of each word. And as an example, we have this strings here. We have cat, dog, car, dog. And when we run the mapping on this data vector with these strings, we get cat is 1, dog is 1, and so on. So everybody is counted once in the first step. The shuffle and regrouping is we take all the cats and sum up the data vector for those. We get all the dogs, we get apparently 3 of those, and we get 2 cars. And the reduce step is just summing in how many you have in each, and then you come to the count vector where we have 1 cat, 3 dogs, and 2 cars. So that would be an example how to do this thing. And as an counting example, just to see how it works, let's load Shakespeare's A Midsummer Night's Dream. And we have the full text here. It's available online if someone wants to take it. And then we read it and print the first lines out of this. And this is what we get, a little vector here. And now we would run this as a serial execution where we count everything, and it took some time to execute, half a second apparently on my computer. And then we would get some information from that. Then we do some printing, and we can see the most frequent words in A Midsummer Night's Dream is not very surprisingly these words here, the, and, I, to, of, etc. The fun words come in the least frequent ones. I don't think most of those are used today. I definitely don't use them. But yeah, so this is what we got from out of 26,000, almost 27,000 words. And what we want to do now is to use this MapReduce approach using DAGs. DAGs is in principle this MapReduce approach implemented in Python, where we have the mapping, filter, folding, and grouping as Python objects. Interesting thing is that this already allows us to run things in parallel, so we can do splitting of the data and allow multiple cores to run this in parallel. And another thing is it executes the data processing lazily, so it only executes the steps that are needed. And can also work on larger than memory data, so if the memory is not sufficiently large on the computer, it could even take on things from the disk. So here we have a little example. This is just a line of 2 words. There's actually an auto test part here where we want to see. We want to extract just different words. And this is now implemented. So the word counting that we did before is now implemented as a DAG from a sequence. All lines, we say that we partition into chunks of 10,000. And then the response here is we've got some DAG with 13 partitions. Then we map the output. We run here this line to words. That was the function we had before. And flattening it. There's still 13 partitions. And then we want to run the reducing. So we want the output frequencies. And we want the top 10, and we want the bottom 10 of the result. And when we run this, we get some execution, and we see that the first approach, the top 10, took 640 milliseconds, and the other part took 528 milliseconds. So it's pretty quick, but it's a different approach, and we get actually the same results as we got before. So this is good. We can also visualize what is happening here, and we have some number of processors running. Here in this case, it looks like we had 6 processors running, and you can see that the memory is running up quite wildly during this processing, and this percent of the CPU is pretty modest actually. So it's not a hard task for the CPUs. So that was one example of how you can do this MapReduce, which is an also similar approach that Google is using for their mapping of web pages. We have different environments. So Hadoop is a system that was developed by Yahoo as a part of the Apache project. So Apache is a web server system, and there they have implemented this. So it can also work with non-local data, and the storage is expanded with the available processing power, and that's actually used by pretty many of the big ones handling loads of data. And so this is also available often on server services that you can buy, and also Swiss data science what is it called? SDS, yeah. Well, anyway, Swiss data science services, they also provide this in their workflow. Another one is also working with Spark. It's a different approach too. Can work with different algorithms, also work on coarse-grained processing, that it can exchange information between different chunks, can do some in-memory caching, and then working on a large distributed parallel computing, and logistics should be minimal with this. And this is also working in a declarative way instead of imperative. So then we have the DAGs, which is a Python pure Python implementation. And the first thing that it's supposed to do is that it's fault tolerant, so it can take care of someone failing, and also that it should be supporting the distributed computing of numerical and Python codes. And what they have put a lot of effort into is to make the libraries that we already have been using, like NumPy, SciPy, and scikit-image. All these are available within the DAG framework. And you can actually very easily change it. So as you may know, when you import something, you usually say import NumPy as NP. Then you could do dask.numpy as NP, and everything looks the same, which is pretty convenient. Let's look at how to implement these codes, and that's usually done using the directed acyclical graphs. So you saw in the first lecture, I had some node diagrams where the processing was going through step by step, and that is actually also implemented within Spark and the DAG, but also in the machine learning libraries TensorFlow and PyTorch, and that's the efficient way for doing all these complex operations. Yeah, and here is a list of different packages that actually support it, and well, you probably know some of them already. And an example of a DAG is here we are starting working with images. We want to work with two images. We have image 1, all elements are 0. Image 2, all elements are equal to 1. And the task array is generated like this. We have here the zeros, and we want it chunk, so we want a 5 by 5, and we want a chunk with the same size. Image 2 is the ones, and same chunk, so we essentially only have one chunk of data to process in this example. And the last line is only about making a graph, and it looks like this. So the variable zeros like is generating a single chunk, and the 0, 0 means that we have that's just the coordinates of that chunk. If we want to do some arithmetics with these, we have the ones and the zeros, and we want to do something on them. Here we do a multiplication, and so actually here you can see the equation that we implement. So these are actually task arrays. So we have image 1 minus 10, we have image 2 times 50. And that is what we are showing here. So here we do the multiplication. You don't see that it multiplies by 50, and then comes same size out, and then we add that, and we get the same size in the end. A little bit more complicated. Now we want to multiply image 1 by image 4, so that was the processing from before. And if we draw that graph, you can see here now it gets a little bit more complicated, but in the end we get our image out, which is the result of this processing. This is not yet so fantastic. We're only working with single chunk. So let's go up working on some image data. So this is some bubbles, a 3D data set where we sum up. This is just a view where we sum all the slices. Here we have 10 frames of the data set, so you can see what it looks like. And if we want to do some processing on this image data set, we have an image which is 100 by 400 by 400, and now we want to work with 20 slices per chunk, and we also want to rescale the data. Instead of having 0 to 255, we want 0 to 1. So now we create this task array from a NumPy array, so that we have the phone stack divided by 255 to get this part. And now we say we have the chunks of 20, and the output now from this initialization is that we have actually 5 chunks, because there were 100 slices in this data set. So now we have 5 chunks, each with 20 in them. And now we want to add a filter, and when we do this, you start seeing that now we get multiple processing, and each can be assigned to its own CPU. And still we have the same chunk, so this is chunk index 4 of the Z coordinates. It's always 0, 0, because on each plane we have the full image size. And now we apply the Gaussian filter, and now you can see this is actually only applying the typical ND image Gaussian filter, and just bring it in here as the mapping function. And now we come to the more complicated thing. When we apply these filters, these blocks are processed individually. So with the boundary filtering for each chunk, but we don't want that, because that would be giving us some strange transition between the blocks. it looks, if you would look at the filtered image, you would see directly that this is block 1, this is block 2, etc., etc. So what we want to do is to introduce some kind of overlap. So we add here a factor 3 times sigma, and sigma is 3. So just to get the boundary processing area. And with that, we get a little bit more complicated, because now we want to get things from the neighbor block and bring that into our processing, and finally do some trimming. So this is what we see here in these overlap and get item parts. So it gets more complicated, but also it takes care actually of the inter-block communication for you. And yeah, here we can see this overlapping boundary, and that is the whole thing here with the overlap. And then if we want to make it more complicated, it starts getting a bit inconvenient actually to plot the whole processing. But here we do first applying a threshold, then we erode with some ball structure element. And here we can see that first it does some overlap processing from the Gaussian filter, then it trims it to do the thresholding, and then afterwards it makes the binary erosion, which requires again some overlap processing, and finally trim it down to the original size. So yeah, looking at the network may not be so convenient when you start doing a lot of things, but the processing as such enables you to run this processing in parallel instead of sequential as it would have been if you run the typical ND image. And then we can also work on labeling the items. And now the problem is that we want the labeling to be globally unique, and that is not so obvious, because if you start the labeling on chunk 1, then you get a certain set of labels, then in chunk 2, you start again from 0, and that's not so easy. And then you still want it to increment the labels for each block. So there you have to find some kind of solution of handling that. Yeah, and then we can run it. And let's run and see. And apparently there is some issue here between the blocks that makes it a bit tricky to handle. So the boundaries when you do labeling is something to pay extra attention to. Then another thing, when you run this, it's the importance of how you run your processing. First part is if you want to select a slice and filter, or if you want to filter and select a slice. You already see in these blocks that this obviously takes less processing power from the computer, as you only take one piece of data. And this, in comparison, requires that you do the whole image before you can select it. The result in the end should be the same, but the question is how long it takes to process it. So here's a little piece of code to execute this. And if we look at it, here I ran it with a single worker, just to compare. And we can see that it took some more time to run it if you do the full volume and extract than if you do just extract a single slice and process that. If you run it with 8 workers, then all of a sudden, at least, we have about the same execution time, but the computer is working a lot more. But anyway, we can, thanks to the parallel processing, we can speed up things. So it's possible to do both, but I would recommend if you can split out and take small pieces, do only the computation that you need. Yeah, and what is happening is if you extract a single slice, then you only process 3 chunks, and if you filter and select, you need to divide into 10 chunks, and all chunks are processed, and the slice is taken from the result. So you can also see from the graph here that a lot more is happening to process this. The reason for the 3 chunks is the boundary processing. It needs to fetch the neighbors to filter. And then, of course, what is pretty common right now is, in particular if you do a lot of machine learning, is that you go to cloud computing, because local resources are expensive. You need to buy it, for one, and also you need people to maintain the system, and you rarely utilize the computer at 100%. And if you use the cloud resources, then the setup is pretty easy, and you can buy in as much resources as you would need. And the whole cluster management is already done for you. And these services, they also provide the common tools that you would need for your processing. So buying in for some tens of francs to do your processing, and then you have your results instead of buying something for 10,000 francs or even more. That clearly says something. The motivation for having the local resources is you want to keep your data for yourself, not sending it out to making it available to other people, even though they claim they have. The data is private. Thanks to different laws, the data could still be available to governmental information. So it can be a good way to get access to really fancy computing resources to work with the cloud computing. And well, for that we have some big platforms. Spark is one that has a lot of these parallelization tools, where it also has all this algorithms already implemented, and Spark is also supported commercially, and many people donate to the project. So Apple, Google, etc. They donate a lot of money to them. And of course, it's an open system, also a lot of academic support, a lot of source code is available on GitHub, and it's also pretty elegant, so it's a compact code piece. And thanks to the licensing, the open licensing, there are no patents or restrictions of usage. So this is an environment that is pretty common to use. Then when you have really large data sets, maybe also during the experiments, you could also go towards the streaming processing, processing more or less on the fly. And then you can do the analysis in parallel with your acquisition, and in some cases even get real-time analysis and statistics, which could be good when you do experiments and want to see the progress of the state of what you're looking at. And also, of course, you can handle static data, but live data comes in and could be done then in real time. Ideally, you should be able to use the same code for real-time analysis as for static coding. And well, should also be scalable, so you can add more computers if you if the speed of the data that comes in is too fast. And then when you come into this kind of works that you have so much data, you also have to restrict yourself sometimes, that you're not only computing the exact volume, that would be nice, but you don't have time to do it, then you can do, for example, doing mean volume within time and say you want it within 5 minutes because you don't have more time to wait for it, or get the mean volume within in a confidence interval of 0.95. And these are things that can be relevant. They are sufficient estimates for real-time processing, but maybe not for the final result. So that are choices that could be thought about when you have really large data streams. Oh, I'm not on the right. Yeah, there he comes. So that brings me to the end. And well, in principle, the message is you can do more when you do it in parallel. The problem is that we have limited resources. It could be also that we have a redundancy. We want redundancy and we want to minimize race conditions. Cloud computing is an option if you don't have your own cluster standing in the basement. And DAGs are a way to handle this. In particular for Python, it's an easy way to get into running your processing in parallel. But yeah, that was about that for today's lecture. But let's just go to the last one. Oops, that was actually the last slide of that one. So just a moment.